Hello, I'm Brian Downing, and today we're going to talk a little bit about prime numbers. Now, when people usually talk about prime numbers, they're talking about something very often that's very elusive, right? Primes are this really rare thing, and we got to find the next super big number, right? And I'm thinking, depending on where you're counting from, that's not necessarily the case. So for instance, when we're dealing with really small numbers, primes are actually very, very common. And here, I'm going to demonstrate this real quick. So we start with 1. 1, of course, is neither prime nor is it composite. So we're going to start with that, 1. Then we go to 2. 2 is prime. And 3 is prime. 4 is composite. Then we've got 5, prime. 6 is composite. 7 is prime. 8 is composite. 9 is composite. And up to this point, if you'll have noticed, primes are actually ahead of the composite numbers. And this point here is where we're actually equal for the first time. So we're just going to draw a little line like that. But we're going to continue on. 10 is composite. Then 11 is prime. 12 is composite. And 13 is prime. And actually, that's it. This is actually the last time that primes and composite numbers are equal. Because we can continue on. We've got 14, that's composite. 15 is composite. 16 is composite. 17 is prime. 18, 19, 20, 21, 22. And you can see that counting forward, composite numbers are going to outnumber prime numbers, and it's not even going to be close from this point forward. So yeah, that's kind of the relationship between the two populations of numbers, taken as it is. But now, when we're counting up towards infinity, something that is very commonly understood is that all prime numbers counting up towards that way are all odd. In fact, the only even prime is the number 2. And if you can see, looking at all these composite numbers, they're actually, the majority of them are actually even. So of course, 2 is even. And then we've got 4, 6, 8, 10, 12, 14, 16, 18, 20. All of these even numbers, right? And we know that we're not going to find any primes there. So it's kind of unfair to compare these two populations of numbers on their own, including the even numbers. So here's a thought I have. How about we compare prime numbers to composite numbers, but we just exclude the even numbers, and then we'll see what that looks like. Let's get to it. And voila. Okay, so here we are. This is the relationship between prime numbers and composite numbers, excluding the even numbers. So we're looking at strictly all odd numbers here. And as you can see, this is the region from where primes have been dominant continuously up to where they're equal for the very first time. And then this lower region is that region of debate where it was equal for the, right before this, up to where it's been equal to the very last time. And this lower region here, I just put a couple numbers down. This is the region from where, from this point on, composite odd numbers are going to dominate over the prime odds forever. And that's it. Very nice little chart here. But there's something kind of curious about it. If you're a nuclear physicist or chemist, perhaps, you'll know some fairly interesting numbers here. As you can see, if we relate this top portion and include the number 1 as well, if we take this top portion and compare it to the periodic table of elements, what it turns out is that all these numbers here represent the atomic numbers of all naturally occurring elements, or at least all the odd ones. They all fall explicitly within this range. And this smaller range here you'll notice that these are actually all the synthesized elements as well. And it's a very kind of curious situation. And in fact, 117 is the last odd-numbered atomic element, or atomic numbered element. And it's really, really curious. And takes us to the very end of the 7th period of the periodic table of elements. And so far, we've discovered nothing beyond that. And that is really right where we're trying to make efforts right now today, is whether or not elements 119 and 120 even exist. So yeah, very kind of curious thing. But it does make intuitive sense, however, because if you think about it, atomic numbers are determined by the numbers of protons that an atom has, or that an element has. And as a proton cannot be reduced to a fraction of what it is, it's expressed as an integer number. And just like prime numbers, as they're defined, they cannot be reduced to smaller integers. Yes, you can reduce a prime to a fraction of something, but that kind of, but that's not the point of what makes a prime. So it's kind of curious that it kind of shares that little relationship there. So things lining up so strikingly, why is this not common knowledge? So here's something else very, very interesting that this lines up with. When you're counting all these numbers up to where they're equal for the very first time, you can see that in terms of numbers of pairs, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 pairs of numbers. And that's really kind of curious because we as humans have 23 pairs of chromosomes. And what's also kind of interesting is even if you want to account for mitochondrial DNA, that little tiny piece of genetic information independent of that, you could express that as the number 1. Very, very kind of striking arrangement there, that this numeric relationship lines up with both the human chromosome count and the periodic table of elements. Very, very interesting, I think. Okay, so yeah, this is really cool. So I've been with this numeric relationship for about 1.5 years now. I stumbled upon it December of 2017. And if you think about it, it's really kind of spectacular, really. You take numbers, right? And the qualities that they have and the relationships that they have with each other, these are absolutely immutable things. And on the other hand, when you take the periodic table of elements, this thing represents the basic building blocks for all of the matter within the universe. So these are two very profound fields, basically, that are coinciding with one another. And that's very, very striking. And I find it very curious that I can't find anything else about this, right? I stumble upon this thing and I'm trying to do research on it, and it's very difficult to find anything about it. And this is something that I feel should be common knowledge, really. And so then, of course, you have this additional coincidence with the human chromosome count. And of course, it's commonly understood presently within academia that there's this big push to keep Darwinian evolution in the forefront of academic thought, really. And it kind of makes you think, might there be something going on there that's inhibiting some kind of fundamental truth? So that's something that's very interesting to consider, I think. So here's my thinking. It is an extraordinary coincidence that our chromosome count would also coincide with this potentially very profound numeric relationship. And I think there's something to that. If you subscribe to perhaps an intelligent design paradigm here, it's almost as though that they wanted to imbue some meaning with the chromosome count. So let's say, like, take for instance the meter, right? That is some fraction of the Earth's radius or circumference. I think it's from pole to pole, but it's some fraction of that distance. And we created such immense importance to have this one commonly used measure of distance, of length at least, and that we derive it out of nature. And now, the planet Earth, it's the size that it is, and, presuming that it's a creation of some random elements of how physics is applied. The meter on the planet Earth, if you define it the same way on some different planet, it'd be a different length, of course. But, all the same, we did everything that we could to, well, if you go by the actual story, not necessarily, but there was a lot of pains taken to make sure that there was this specific measure of length derived out of nature. Now, if we look at the nature of the periodic table of elements, and as it relates to this numeric relationship, perhaps the same kind of consideration was considered to, that consideration was made by our potential creators here. So I think that is a very strong possibility of evidence that as a species, we were created, or if perhaps evolution does in fact still apply, perhaps we were monkeying around with our DNA at least, such that it would match up. That's also a possibility, although I'd like to think that, really DNA may not even be a natural construct. It might actually be more considered to be really like a nanotechnology, actually. So that's something actually kind of interesting to think about. But yeah, that things match up so strikingly, it's definitely worth pondering about. So yeah, so some really, really interesting things here to consider. I think I've left you some nice, interesting things to ponder about. Yeah, and if this is stuff that you think is important, elevating the visibility of these subjects, if you'd like to like this video, of course, leave a comment, subscribe to my channel is also very kind of you. But yeah, sharing these ideas, sharing these with your friends and your family, and just getting the word out, that's going to be very important for ideas like these moving forward. So yeah, I gotta thank you so much for sticking around and joining me on my journey here, and I'll see you next time.